what else? I guess that was the only one. That's the only formula, I guess, wave speed for a rope. Is the one we went through. I would not expect you to work that out on the exam. I would have it written on the exam. But let's see. Standing waves. Standing waves are important because if you want to figure out, suppose you're asked about the frequency of some wave is, how do you figure that out for some pipe organ or whatever? Well, the first thing you do is figure out what the nodes are going to be, and there'll be something else in the problem description to tell you, how many nodes should there be between the endpoints, right? So if it says what's the lowest frequency sound or the second lowest frequency, right? Okay, there's this harmonic structure, right? There's the longest wavelength you can cram into some particular set of constraints at the boundaries. Like for example, if you have a rope, well, if you have a rope that's tied on the wall over here and tied over here, it's got to be like this is the longest wavelength I can attach. You guys get this, right? The longest wavelength you can attach. Here it is going up and then going down, right? Between these two endpoints. So this is the fundamental or the lowest frequency associated with that. It's moving down with the smallest frequency. How would you calculate the frequency? Well, if you know what the length is, you figure out the wavelength. What is the wavelength? 2L. And then using these sort of equations, you can figure out what the frequency is, right? Because you'd need to know what the physical situation is. If it's a rope as opposed to air molecules, you have to know what the formula is for the velocity for a rope. You'd plug that in to this, right? Or to this, and then relate that to lambda, lambda f, and then you can solve for your f. Now, when you want to know what the frequency of the sound is, right? Like what frequency am I hearing? What we're looking for there is f, is cycles per second, right? So when people talk about the note of an instrument or whatever, they're talking about how many cycles per second, not radians per second. Anyway, so you get the same picture for standing waves in a box of air, where what we're applying now is the displacement of the air, and you get these sort of pictures, right? So there's only three cases you really have to consider. You probably already figured this out, but there's only three cases you have to consider. There's the case where both sides are closed, which is the same as the case of a rope, where it can't move on the ends, tied on. So it's exactly the same, right? Lambda is 2 times L, lambda equals 2L over 2, which is 1L, right? Lambda equals 2L over 3, etc. So, in general, lambda is 2L over N, right? Where N is 1, 2, 3 to the ends, right? And similarly, if it's open on both sides, you get the same exact progression, right? Because this is exactly half a wavelength. Oh yeah, if it's open on the side, that means that you're at an antinode, the place where the air can move the most back and forth. So then you have to have at least one node someplace. You can't just have straight across and there's no wave. So it's frequency equals 0, right? Anyway, all right, I think you guys know what to do with that, and so on. And so that's exactly the same as what we have down here. This gives exactly the same progression of lambda versus L sort of relationships. And then there's the one oddball case, right, where it's open on one side and closed on the other. That's when you get something that's really different. So what's the relationship here? How long is lambda here compared to L? Is lambda bigger than L or smaller than L? Bigger. Is it 2L? 4L. I agree. And then the next one. Anyway, you guys know how to do this. That's 1, 2, 3. So now you have 3. So it's lambda is 4L over 3. Anyway, and so it goes. So you get 4L over N equals 1, N equals 2. So it's interesting. There's 4 different physical situations we're describing here, and yet there's only 2 sets of equations. So and you can see why, right? You go through it. And the reason instruments sound different is because they have different amounts of power associated with the different levels of the different harmonics. I never did write down the rope speed. This is what I was referring to before. So from the physical situation, you know what the speed is. If it's a sound wave, for V, you just use the speed of sound, and you'd be given that, or you calculate it from some other part of the problem. But for a rope, you actually have a formula, and you don't have to derive it, right? It's sort of silly because we use different notation to avoid T for sort of putting tension here. I mean, this is the force you're pulling the rope with, so it's just the tension in the rope. And of course, you're dividing by something that's like mass, right? Mass goes in the bottom, force goes on top. This is the mass per unit length. Usually I'd use lambda for that, but we've already used lambda for wavelength, so it's already been used. Okay, good. So one topic that comes up on lots of exams, like I said, I haven't written the exam yet, but the thing that shows up on lots of exams is Doppler shift. You've had some Doppler shift problems. You've had a couple challenging Doppler shift problems on homeworks, right? Where there are moving objects and moving sources. You have to think through how, like, you don't always have the clean situation where there's a stationary source and a moving observer, right? And you just plug into that formula. Oh yeah, U is the motion is the speed of the observer, and V is the wave speed, and just get your plus and minus sign right based on whether it's, in all cases, you choose the plus and minus so that the frequency you wind up with is bigger if the two are getting closer together with time, or smaller if they're going further apart with time. So just choose the appropriate sign to make that true, right? Doesn't matter if you're moving toward the cop car or she's moving toward you and you're holding still. Either way, the frequency will sound higher pitched than it would if you were both stationary, right? So then choose the sign to make that true, right? If you're getting closer. But if you have more complicated situations, you got to break it down, right? And so like that problem's pretty complicated. You probably won't see something that's that complicated on the final. But anyway, the first thing to do is to recognize when you've got a problem that actually involves a Doppler shift. And the next thing is to figure out, okay, who's moving, who's holding still. And when I talk about moving and holding still, so in much of this class, in physics, right, I told you in the beginning class that velocity, like any Galilean reference frame, any what's the right word? Inertial is the right word. Inertial reference frame, right? For Galilean, for plain old Newtonian physics, Galilean stuff. So forget Einstein, forget that kind of relativity. Just with plain old F equals ma. F equals ma is true no matter what reference frame you're in, right? So somebody who's watching the whole scene going by in a rocket ship moving at some fast speed compared to the Earth, as long as it's relativistic speed, as long as it's not your speed of light, F equals ma works just fine. So why all of a sudden do we have equations where speed matters, where depending on who's moving and who's not moving, why should that matter? And the reason it matters is that the air, the medium in the room or outside that's transmitting the wave, that provides a special reference frame that you have to think about. In other words, there's actually 3 things going on when you've got someone emitting a wave and then some observer that's hearing the wave, right? That third thing is the medium that's transmitting the wave. So that's why we talk about whether something's holding still or moving. They're holding still or moving with respect to the air, with respect to the water, with respect to the thing that's transmitting the wave, right? So that's why we have these equations when it comes to Doppler shift, where it actually matters what your absolute velocity is. It seems kind of strange. Well, actually, it is a relative velocity. It's relative to the medium through which the wave propagates, right? So that's why this Doppler shift seems separate from the rest of the class in that respect. So, and we got 2 equations for that, right? There's the one where the source is moving, right? And let's say wave speed here in all cases, we're going to say that's V. We've got an observer over here. We've got an observer. I think they put V over here and A over here for reasons I can't explain in the book. So it's all right. In this case, the source is moving away from the stationary observer. I know that, will he hear a higher pitch or a lower pitch than he would have experienced had everybody been holding still? Lower pitch. That's right. And so what I get for that is, see which ways it goes. It's going top to bottom. The moving source has that funny factor in the bottom. So I get the frequency here is equal to the frequency that's being emitted if everybody were holding still times, divided by 1 plus or minus. And it's always going to be U over V, right? And the way I remember that, I'll leave it written down on your sheet, but the way to remember that is that these things make the most sense, or they're sort of easy to think about when the speed of the observer, or in this case of the source, right? U, the speed of the, I should be really clear. Here, let's do this. So V is wave speed. So these are all going at speed V, but the source himself is moving at speed U, okay? All right. So u is smaller than v is the normal situation. If a police car is moving faster than the speed of sound, you don't hear him until he's right on you, right? Then he's going over 300 miles an hour. So that's not the usual situation we're experiencing. Usually u is smaller. These equations still tells me in that case, but anyway. So anyway, good. So that just reminds us that's going to be a smaller number. So it better be the case that you're. Well, I shouldn't say that. There was a problem in a past final or midterm where there's something on a jet ski and he's moving faster than the wave speed, right? And you can think of that as a Doppler shift problem. I didn't solve it that way in my solution set, but you can think of that as a Doppler shift problem, right? Where he's not hearing the wave, he's actually experiencing he's being bumped by the waves as he goes along. Well, if he's going faster than the speed of waves in the medium, he's moving away from the source. So in this case, the waves are coming into the shore. The source is some distant storm in Japan that's causing waves to come in, police the surfers, right? So here comes a bunch of waves, surfers here anyway. They're coming in, and so if you're moving toward the shore faster than the wave speed, right? So that's a case where you can think of the source as being stationary and the observer, the guy on the jet ski, he's moving. Well, so that's not this case. This is the case I'm going to draw over here. In that case, you are going to solve this. You are going to solve one of these sort of equations in a case where u is bigger than v, right? But it still makes sense, right? You're catching up. The guy's catching up to waves that were emitted earlier in time. In fact, if you went faster than the speed of sound, and you were actually able to hear anything doing that with your ear out the cockpit window, what you would hear is the sounds that are being emitted by things behind you in reverse. You'd hear them time reversed, right? You'd be catching up to the first thing I say. So I'm talking and you're getting way as fast as you can in some jet plane, right? That's Mach 2. You'd hear me talking backwards, normal speed, but talking backwards, right? Because you'd be catching up to earlier wavefronts. So anyway, for what use that is to how you think about this stuff. So I'm talking that's a case where you've got a stationary source, but I forget which way the book drew it and see if I think v is going that way at speed u and a is going that way at speed u, right? And the wave speed again is v and v, right? So in this case, yeah, you get this times 1 plus or minus u over v. So in these cases, they're getting closer together with time. It's going to be a higher pitch sound. Means I better use the plus for b, right? That's how I think it through. Opposite over here better be a minus for b because that'll make this number smaller than 1 and it'll make the whole thing bigger than 1. It's a bigger frequency. Yeah, that sounds right. Oh, I'm sorry. No, I said it exactly backwards. He's moving that way for b. So in that case, they're getting further apart with time. Pitch goes down. F prime is smaller than f, right? That means this better be the plus. Anyway, that's how I think it through. The thing I was thinking about hearing somebody talk backwards, if u is twice as big as v, then you're catching up to wavefronts that were emitted earlier after you run into the more recently emitted waves, right? That's just like that surfer moving toward the beach on the jet ski going faster. I guess he's not a surfer, he's a jet skier. But he's going faster than the speed of waves on the water. Okay, and so and you can use that formula to get that. You just get a minus sign when you're done if you do that. I didn't solve it that way, but you could just plug it in that formula. So what else can I tell you? Oh yeah, intensity. You know what the definition for intensity is? You have waves, sound waves. Intensity is that's just the amount of power distributed over some amount of area, right? And if you have a sound wave being generated by a stationary object and it's going out in equal directions in three-dimensional space, you'd say, oh well then that looks like the total power, right, from the source over the area of the surface. That's 4 pi r squared, right? So power falls off like 1 over r squared. Thank goodness. That's why when somebody drives by my window with their loud radio going, if the street's twice as far away, it's 4 times quieter, right? So it doesn't fall off linearly. It falls off faster. It's a good thing. Okay. So people have questions about waves and stuff. Should I keep blasting on? Forward. Yeah. All right. Cool. Fluids. Fluids will be on the final for sure. And there's only a few equations for fluids. And there's a few places where students often and professors get confused. In particular, like a continuity equation. That's an important equation. Right, the continuity equation. So there's two forms of that. One is for any old fluid and one for incompressible fluids. Continuity equation says that some density of fluid times, let's do it this way. Let's draw a picture. We have some pipe, right? Maybe fluid's coming in over here at some velocity 1, and there's some area of the pipe right here, and there's a density of the fluid. So I'm using 1 to indicate this location in space. That's almost always how I do it with fluids. I use 1, 2, 3 to indicate different points in space, and say, oh, if I have some flow, some continuous flow, all the fluid that comes in here is going to come out over here. So that means that, here's my V2, here's my A2 is the area of that the hole right here, right? And then I've got what else? Oh yeah, rho 2. So rho might be able to change if you have air going through it too. Air is compressible, right? I mean, to a good approximation, it's not. So when you solve lift on a wing, and engineers calculate that, we often assume it's incompressible. But you can compress air, so rho could change. No problem. Yeah. Yeah. Okay. So it's a technical question. How do you avoid p's and rho? How do you watch your p's and rho's? And the way you do that is when I write p for pressure, I put a serif on there. And when I do rho, I draw it like this as a continuous line. And certainly, so in terms of the exam, you should be able to tell the difference. Usually, I'll say the density is, and then I'll write rho. But you can see based on it, it'll be in some typeface where it's really clearly distinguished, right? Sorry. Oh, what am I doing? Was I about to write an equation? I was about to write an equation. So this is pressure, and this, yes. So the way to distinguish them is the serif on there is for pressure, and all I was about to do is write the continuity equation. Continuity equation is rho 1 times v1 times a1 equals rho 2 v2 a2, right? That just says conservation of stuff, right? Whatever comes on one, or conservation of mass. Whatever mass of water comes in over here in some finite amount of time, for the same amount of time, the same amount of water come out over here. Unless you've got some balloon on the side, it's accumulating fluid, right, or something. And because for an incompressible fluid, right, rho 1 equals rho 2 for any 2 points along the flow, well, that means that the continuity equation simplifies into v1 a1 equals v2 a2. Now, is this still true if I have viscosity in the pipe? Suppose I have suppose I'm putting molasses through here, very viscous type of a fluid, right? Is the continuity equation still exactly right, or do I need to have some kind of correction term or something? Sorry? It still works. That's right. It still works. And the reason it still works is that mass is still conserved even for molasses, right? It doesn't matter if the stuff is really sticky and if you're losing energy. Well, that's what can happen. You can lose energy. And that's why the Bernoulli's equation can be affected by viscosity. So if there's no viscosity, if you're not losing any energy due to dissipated forces, you've got Bernoulli's equation, right? Bernoulli's equation just says now I'm going to be really careful with my p's and rho's. I got my p, p1 plus rho 1, rho g h, right? And now I've got my kinetic energy term 1/2 rho v squared, right? That's a constant. So this is the same thing at point 2, right? Rho 2 g h2. Well, this is only true if you're not losing energy due to viscosity, right? Or some other dissipated type force. If you have viscosity, you can lose energy, and the thing is, because of the continuity equation is still true, it tells you that if you know what the area is of your pipe on the one side, area on the other, and you know it's an incompressible fluid, well, you know what the velocities have to be. Well, we say it this way: if you know the velocity is on one side, then that guarantees you know the velocity on the other side, right? A1 times v1 equals a2 v2. That's all there is to it. So if you know what the two a's are and you know what the velocity is on one side, the velocity on the side is fixed, even if you've got dissipation. But if there's some dissipation due to viscosity, where does it come from? Well, it can't come from the v's; those are fixed by continuity. It's got to come from the pressure, right? So when there's viscosity in a hose or something like that, in a water hose, the place that the energy is coming from is from the pressure. That's where it all comes from. So if you have some other independent information on how much energy was lost, that's where it came from, pressure. And the rest of it is given by a continuity equation, right? What else do we know from this? Yeah, so Bernoulli's equation, continuity equation. There's not that many equations. There's just definition of pressure, right? You have to know force over area is pressure. You have to know how to use that. And of course, this is in itself a really important equation. It tells us how it is that you can lift out something really heavy, right? Just with a small force over here. This is a large area. This is a small area, right? Then, well, we know that the pressure. So let's see. How do I relate these things? If this is one continuous container of oil, it's one continuous flow. In fact, it's not moving right now. It's in static equilibrium. It's not flowing. It would still be true if it were, but let's make our life simple right now. And I say, okay, I know the pressure right here, P1, right? Well, is it going to be bigger or smaller than the pressure down here? This is a lower height over here. So is P1 bigger or smaller than P2? So who thinks P1 is bigger? Who thinks P1 is smaller? Who thinks P1 is the same? Well, there's a non-zero height here. I got like one vote apiece for those three options. So this height, right? This is height h. One of them was true. One of you was right. So there's a height right here, right? It's non-zero. That means that there is a difference in the pressure. There's no motion going on, right? And so if you go higher up in a pool, even if it's of oil, you got less pressure. You go bottom of the pool, it's more pressure. So P1 is less than this. We'd use Bernoulli's equation to relate those two, and we'd say, oh, rho g h. And what rho do I want? I want rho of the oil, whatever this fluid is, it's oil. But it's the same everywhere. It's an incompressible fluid, so rho is the same everywhere. Let's say rho times g times that height. Well, that plus P1 had better equal P2. That's just Bernoulli's equation, right? If we then ask, all right, well, then what about the pressure? What about the force I exert up here? Well, I'd say, oh, the force up here, what's the force that this is exerting upward? Force 1, as opposed to force 2. Well, force 1 is just going to be equal to P1 times A1. Anyway, you get the idea. You don't have to do this stuff, but just to jog your memory. So I'm sort of showing where these things come from. That's how you think it through. Viscosity has no effect here because there's no motion. Viscosity only plays a role when things are moving, when there's flow, right? But anyway, what is that equal to? Oh, yeah, by this equation I can just say, oh, that's just equal to P2, which is 1 atmosphere. So oh, no, that's not necessarily true. If there's a car on top of that, then P1 is not going to equal just 1 atmosphere, right? I see my ones and twos confused. Let's see. If I want to represent this in terms of the other, suppose you know what F2 is, how would you relate them? You'd say, oh, this is equal to, say, what is P1? P1 is P2 minus rho gh. This is all times A1. Say, oh, but I know that P2 times, P2 times P2 times A2 is F2. So I'd say, oh, that's just F2 over A2. Good. So now I've got an expression that relates the things I know to the thing I want, right? So this is how you relate F2 and F. Anyway, you get it. Yeah, buoyant force. If I'm standing at the bottom of a swimming pool, so I go into a swimming pool, I exhale enough so that I'm slightly denser than the water, I sink to the bottom, stand on the ground. Do I still experience a buoyant force from standing on the bottom of the pool? Yeah, which way is the point? Always points up. In fact, if something is floating, right, it still experiences a buoyant force, but it's only, well, in fact, something is floating, it's just sitting there, it's not sinking, it's in static equilibrium, it's just sitting there floating. It has a total volume, total V, right? Well, if I wanted to make a three-way diagram of this thing, right, what do I say? I'd say, well, it's got an upward force due to buoyancy, F sub B, downward force due to its gravity, and by that I mean gravity acting on this mass itself, right? If it's just floating there and it's not going up or down, it's not accelerating in either direction, by Newton's second law, acceleration equals to 0, so I'd say, oh, that means that when the dust there is FB, the magnitude of FB equals the magnitude of FG, right? These are the same thing. So then how do I relate that? How do I know how submerged it is? How do I know how high it sits in the water? How do I calculate those things? Just to remind you, the volume here that matters for calculating these forces is different for the two cases, right? For the buoyant force, it's only the submerged volume. It's only this part for the buoyant force. But for the gravity force, right, it's the whole thing. So that's why that's how you can make these things the same, even though the densities are different. The buoyant force, what is that? It's rho of the fluid, right? Whatever that is, times the submerged volume, right? Submerged times g, right? Because that's the mass of displaced water times g. That's the gravitational force that would have acted on the water had this been full of water right here. And then you say, oh, and that has to equal what? It has to equal Fg, the gravitational force, and that's just the total volume, right? The total volume of the object times the density of the object. Anyway, you guys know this. You know all these things I know. Is this useful? Should I keep going this direction? What else should I do with fluids? I'll mention one more thing, and that is center of mass versus center of buoyancy. Center of buoyancy is just where the center of mass would have been had that volume been full of water, right? So what's the center of buoyancy for this thing? Well, it'd be right here, right? It'd be the center of the volume of displaced water, right? In other words, if I were to assign, I'm saying, where is the force acting? Where's the buoyant force acting, right? That's where it's acting. That points straight up. Where's the force of gravity acting? It's acting at the center of mass of the whole block, right? Just like right there, or something like that. Anyway, so that's yeah.
So for the center of buoyancy, you can always just kind of look at the object as like the part of the object is submerged and try and find what would be the center of mass for that part of the object.
So I don't know that you're going to be asked that, but that's how you go about it. Sure, if you're not told. The thing is, to make a boat stable, right, what you want to do is have the center of mass be lower than the center of buoyancy. You want the upward force acting more toward the top of the boat, and the downward force acting more toward the bottom of the boat. How do you do that? You make your boat wider at the top and heavier at the bottom. You put lots of mass, you put plutonium at the bottom of your boat. Actually, they actually do put uranium at the bottom of boats, military boats, to make them really heavy. It's a very dense material, right? As you can see. So you put it way down here, and then you get your center of mass real close to the bottom. The downward force then is pulling down here, and then you have the buoyant force way up here because there's a lot more volume up here than there is down here. So, but this would be too nasty to calculate on exam. But anyway, that's the idea. This is what you like, the force of gravity down like that, force of buoyancy here. All right, let's so fluids. What else is there? That's pretty much all the. I guess the last thing I'll say is if you want to calculate the buoyant force on something, I just did it really fast here, but in general, it's just the submerged volume times the density of the fluid times g, right? And that calculational trick works even if the amount of fluid displaced is less than that. A battleship in a bathtub, it still works. Let's see, what else do we have? Thermodynamics. Yeah, so